Hey everybody, this presentation is really about groundwater, but to start groundwater, we have to start with a water cycle. So the Earth's water is constantly being cycled between the oceans, land, and atmosphere in a process called the water cycle. You're part of the water cycle, right? You drink water, you give off water, you fit right into that water cycle. So water enters the atmosphere by evaporation and transpiration. Transpiration is like evaporation, but it's the water released by plants, by living plants. It's part of their exhalation of water. So we combine these terms and call it evapotranspiration. So that's what we'll describe water from the land doing. Water leaves the atmosphere by condensation and precipitation. We take a look at this. This is the great water cycle, simplified, but water evaporates or transpirates, gets into the air, eventually it condenses, precipitates, comes back down onto the land, and what happens when it gets down to the land is kind of what we're talking about today. Most of the water in the oceans results from
groundwater. Water that infiltrates the soil is pulled by gravity as far down as it will go. Well, it's not going to go all the way down because eventually it's going to reach rock that it cannot penetrate. Deep underground, the rock gets very pushed together and it has no porosity, has no pore spaces. So the water obviously can't get into it. That would be impermeable rock. The zone of saturation, from the level of the impermeable rock to the top of the zone of saturation, is filled with water. The top of that zone of saturation is known as the water table. Now, why is this important? Because groundwater is good drinking water. Almost universally, the best water you're going to get is water you take from the ground, much cleaner than surface water. So if we look at this diagram, we get a sense of what the water table is doing here. So if you look at all the area under here, it's in the zone of saturation. It's filled with water. On top of that, you have all this area here that the pore spaces are filled with air. So the water would percolate, would trickle through that, but would keep going down, pulled by gravity as far down as it can go. If you take a look at the stream here, well, that stream is where the land intersects the zone of saturation. So the stream often is at the is right at the water table itself. And that explains why a stream can keep running even though it's been dry for a long time, because it's taking water from the groundwater itself. Porosity. Porosity is simply the amount of open space in rock or soil. How much, normally it would be filled with air. So how much porosity something has, well, it depends on the shape. Rounder particles have larger pore spaces between them. If you pack the particles really tightly, you get rid of some of the pore spaces, obviously. And if you have the same size particles, you have more pore space between them. But as soon as you mix the particles, the pore spaces that would have been between the large sediments, those pore spaces are now filled with smaller sediments. So no matter what the size, if they're all the same size particles, they have the same pore space in it, whether they be fine sand or large cobbles. If they're all the same size, they should have the same pore space. But as soon as you mix them, they do not have this. They have less pore space. Clay has very low porosity because the grains of clay are angular and they can stick very, very closely together, leaving very little room for empty space. Rocks that have a lot of cementing material, well, again, that empty space may be filled with that cementing material. Particle size. Porosity is independent of particle size, whether it's big grains or small grains altogether. As long as they're the same size grains, you have the same amount of pore space. But here's what you get if you mix the grains. So if you look on top here, look at the pore spaces here. Big pore spaces. If they were small particles all stuck together, they'd be smaller pore spaces, but there'd be a lot of them. But look here. If you have pore spaces and you have mixed sediments, inside those pore spaces between the large sediments, you're going to have the small sediments. So it'll kill the pore space. So as soon as you have mixed sizes, you do not have much pore space. Other ways you might have pore space in non-sedimentary rock, well, if you have fractured crystalline rock, sort of like this granite, you're going to have pore spaces there. If you have limestone, the limestone might get all eaten away by the acids in the water, so you'll have spaces there. Another concept, permeability. Permeability is simply the ability of a rock to allow water to actually pass through it. The rate of permeability depends on the size of the pores and how well they're connected. If you imagine very large pores like in gravel, it's going to let the water go right through it. They're well connected and they're large. Sand would be the same. Large, well-connected pores, very permeable. It'll let water pass through it. On the other hand, clay has very small, poorly connected pores. It is not very permeable, and we're talking not very permeable at all. It will tend to hold water back tremendously. So infiltration is the seeping of water into the ground. Runoff is it running off over the ground. Infiltration will be favored if the soil is unsaturated. Dry soil will allow water to seep in. If the soil is permeable in the first place, if it's not clay soil, if it's sand or something like that, infiltration can occur. Runoff is favored when the soil is saturated. The soil is already full of water, it can't take any more. If the soil is impermeable, in other words, if it's a clay soil, not going to let much water in at all. If the slope is steep, that will tend to have water running off to streams. And if the ground is frozen, frozen ground does not allow much water to seep in at all. So that will favor runoff as well. Capillarity, another idea. Capillarity is the ability of a substance to draw water upward. Now, if you think of a very fine fabric, it will draw water way up it. If you think of a coarse textured fabric, it will not draw water very far up it. So this same sort of thing happens with pore spaces. Capillarity is obviously working against the pull of gravity, and it functions because water is sticky. So water sticks to things and can be drawn upward just because it's so sticky. So water can be pulled up a distance from the water table, and this capillarity may allow that water to be available for plant roots. Could be very important in some areas. Cone of depression. Think of drilling a well, like this well here, all right? So you have a well and you start extracting a great deal of water from it. The water under the ground is not going to flow very quickly to fill in for the water you've removed. Therefore, you will have a cone of depression around a well that is pulling out a good amount of water. It might even lower the water table in enough of a way to make water unavailable for other wells that used to have water in them. So when we draw so much water from the ground, it might have a serious impact on the level of the water table. And certainly the level of the water table right around the pipe where we're drawing it from, the well, is going to go down. That is called the cone of depression. Because groundwater is an important source of drinking water, we have to worry about when it's contaminated. So if you have open space like you do here, you might have septic water basically flowing right down to a well. This would be bad. In normal situations, though, like this, the septic water will flow through a good long way of something like sandstone, all the bacteria down there will chew up all the organics in the septic water, and the water you get out of your well is perfectly clean drinking water. But it needs to go through some amount of sandstone in order for it to be filtered like that. If it flows directly, this could be a problem. Thanks for watching.